Okay, so as you remember from 3.6, example 7, we managed to solve with the new form of elimination, just kind of using the knowledge that we have already and using it in a slightly different way. Hopefully that made sense. If not, if you're looking for another method of solving, or if you're just looking to push yourself a little bit and try something a little bit new and get a bit of extra know-how before when you go off to university, then this video is for you. So we're going to try and solve this again, and we're going to start solving the exact same way. We're going to do our two usual tests. We're going to test to see if the normals are scalar multiples and if they're coplanar. We already did these, so I'm going to fast forward through them. We said that they're not scalar multiples and that it's not coplanar. So that information tells us that the only possible solution is that they intersect at a point. And if you don't recall why that is, go back to the start of the second half of 3.6 when I explained all the tests that we have and all the different types of solutions. But for right now, we're going to say it intersects at a point, and now we're going to go into our new solution. Now, this is going to look very, very bizarre right now. We're going to use something a little bit different. It's something that you probably haven't seen before in high school, unless your data management teacher is really good and has given you a bit of extra information. And we're going to use something that's called matrices, or a matrix. Matrices is the plural of matrix. And what it is, it's a two-dimensional representation of a particular problem. In this case, we're going to represent our three equations, our system of equations, as a matrix. And all we've done here, what we're going to do is we're just going to start with these rectangular brackets, and then we're going to have one row for the x coefficients, one row for the y coefficients, one row for the z coefficients. Then we're going to have a little line in between to represent the equal sign, and then we're going to have our d values on the other side. But because d is usually on the left side of the equation, we're just going to flip the numbers. So that's what we've done here. So the first, in this matrix here, the first column, 2, 3, 1, is all of our x coefficients. 2, 3, and 1. And then we do the same thing for the y's. So we have 1, 4, negative 2, and that becomes 1, 4, negative 2. And then for the z's, we're going to do the same thing. 6, 3, negative 4. And then lastly, we have to put in the d values, but because they're usually on the other side of the equation, we're just going to flip the signs. So that becomes positive 7, negative 8, positive 9. When we write it into our matrix. So positive 7, negative 8, and positive 9. Now this doesn't look super useful just yet. The reason why we do it is because it's just a nice, easy way of getting rid of all the extra stuff. We know that the ABCD is the important stuff to help find the intersection. That's what's going to determine what our point is. And the reason why we do this is because we have some tricks that we're going to show in just a second. But if we manipulate this in just the right way, we can actually take it and rearrange it so it looks something like this. This is our end goal. So this is what we call reduced row echelon form. Now, reduced row echelon form is really, really important. And the reason why is, again, these three lines are going to represent three equations. And in this case, the first line is going to represent, that's 1x plus 0y plus 0z equals some number. The second one, actually, before we go to that, let's rewrite this a little bit. We know that just means x equals some number. Now take a look at the second line. We have a 1 where in the y column, that's going to be y equals some number. And for the third line, we have a 1 in the z column. So that means z is going to be equal to some number. So essentially, if we can get it looking something like this, we essentially have discovered our three coordinates for our point. Now, The tricky part is you need to learn the rules on what you can do with the matrix. So, just like with equations, there's a few things that you can do, and we're going to treat each row like it's an equation. So the first option you have is that you can multiply or divide a row by a factor. Just like we can with an equation. We can multiply a whole equation by 2. It's still the same equation, and we've just multiplied everything. Or we can divide everything by 5, if it makes sense in the problem. So option 2 is that you can add or subtract 2 rows with each other, just like you can with 2 equations. Essentially, that's all we do with elimination. We're just adding or subtracting 2 rows. Sometimes we're multiplying by a factor as well. But essentially, those are our 2 big things that we can do in this. So I'm going to show you the matrix way of doing it, and on the side, I'm going to show the algebraic equivalence. So what we're essentially representing here. So essentially, all we're doing as we go through this is we're trying to get everything into that reduced row echelon form. So what we're going to do is we're going to start chipping away at all of those numbers that aren't on the diagonal, and we're going to start using those rules to help turn them into zeros. So you can start wherever you want when you're doing your own solution, but let's start by taking this one and let's turn that into a 0. Again, you can start wherever you'd like, but we're just going to do whatever makes the most sense. So in this case, let's see, what can we do here? I think if we're taking a look at this, take a look, we have a 6 and a 3. We said that we can multiply and we can subtract numbers from each other. So if we turn that 3 into a 6, then we could just subtract the first 2 rows from each other, just like elimination. Again, it's going to look a little bit tricky as I do this, but I'm going to try and explain as best I can. And as we keep repeating these processes over and over, it should hopefully make a little more sense. So step 2, we said we want to get that 3 and turn into a 6. So what we're going to do is we're going to take row 2 and we're going to multiply it by 2. So if we look at row 2 now, everything from row 2, from step 1, is just multiplied by 2. 3 becomes 6, 4 becomes 8, 3 becomes 6, and negative 8 becomes negative 16. So now that we have that, if we were to subtract those 2 equations, then that would work for us. So that's what we're going to do. So in the next step, we're going to take row 2 and we're going to subtract row 1. So all we've done is, if we take this 4, this one down here, all it is 6 minus 2. If we take the 7 next to it, becomes 8 minus 1, and so on and so forth. 6 minus 6 is 0, and negative 6 minus 7 is negative 23. So just really quickly, let's clarify that a little bit. So let's talk algebraically about what we did there. So we said in that first step, we multiplied by 2. So essentially all we're doing is we're taking plane 2, the equation, and we're multiplying everything by 2. So it's algebraically, that's how that would look. And then in the next step, we said we're subtracting the 2 equations. So plane 2 minus plane 1, essentially it's just basic elimination. So again, that step works. So I won't go through it every single time, but just follow along with the algebraic side if you want to see the algebraic explanation as to what I'm doing with each of these steps. Okay, so now we've gotten rid of one of our 6 non-diagonal entries. So we are 1 down and 5 to go. So now that we have that, let's pick another one. Again, you can pick whatever you'd like. let's go with the 6 this time. So now that we have that, now that we picked that out, let's try to figure out how we can get rid of that. Now, since our second equation is 0, that's not going to help us very much to get rid of it. So we're going to have to use the third equation. So something with this -4. So we're going to have to make those two numbers the exact same for this to work. So we could multiply that row 3 by 1.5, but that might get a little messy. So let's just take both 1 and 3 and multiply them by different numbers. Let's take row 1 and multiply it by 2, and row 3 multiply by 3, and that way we end up with 12s instead. But don't forget, every single number has to multiply. So everything from row 1 multiplies by 2, and everything from row 3 multiplies by 3. And again, we're just taking those two equations and multiplying them by a scalar value. Everything multiplies, so again, we know they're still equivalent. So, next step, now that we have 12 and -12, we can add 1 and 3 together, which is what we're going to do in the next step. So in row 3, row 1 and row 2 are going to stay the same, but row 3, we're going to add in the contents of row 1, and we get, oh sorry, I misspoke. We're not doing that in row 3, we're doing that in row 1. That's the one that changes here, because we want to get rid of this that 12 and return to a 0. And when we do that, we get 4 plus 3 equals 7, 2 plus 6 equals -4, 12 plus -12 equals 0, and 14 plus 27 equals 41. So now we've gotten rid of 2 of the 6 numbers that we need to get rid of. So we're 2 down, 4 to go. So again, you can pick whichever one you'd like. Honestly, it doesn't make too much of a difference. Let's go with this one this time. So again, we have to pick two. We have to make 2 rows equal for those x's to cancel out. So you can pick whichever one you'd like. Go with 2 and 3, but I'm going to go with 1 and 3 this time. Sorry, 1 and 2 this time. So next step, again, we have to make those 2 numbers equal. So let's find 2 numbers that we can multiply the rows by to make this work. So I think if we were to just multiply both of the entries by the other one, so take the 7 and multiply by 4, and take the 4 multiplied by 7, then that should work for us. So that's what we're going to do. So we're going to take row 1, multiply it by 4, and row 2 multiply it by 7, and we get 28, -16, 0, 164, 28, 49, 0, -161. And again, we're just multiplying those 2 equations by a scalar multiple. Now that the x values are the same, now we can just subtract the 2 rows, which we're going to do in the next spot. So we're going to take equation 2 and subtract 1. So now we have 0, 65, 0, and -325, which essentially is just elimination. And when we rewrite that, that becomes 0x plus 65y plus 0, z equals -325, or 65y equals -325. So you could just divide out by 65 to help find the answer there. So that's what we're going to do next. So we're going to take, I got cut off on my PDF here. We're going to take row 2 and divide by a factor of 65. And that becomes a 1 in the middle, a 1 in our y column, and then we have -5. So essentially what that means is y equals -5. So we're actually a third of the way towards a solution. or half of the way if you were looking at the number of zeros that we found, because we need 6 and we got 3. So now that we've done that, now we need to pick another 0 to get rid of. So let's pick another one. Let's go with maybe that negative 16 up at the top. So let's start working to get rid of that. In fact, the nice thing is once we have that 1 in the middle, it's very easy to work with. But row 1 is all big numbers, so let's see if we can do something about that. I can see they all divide up by 4. Let's take row 1 and divide by 4. And then we get 7, negative 4, 0, and positive 41. So now that we're getting good with this, I'm going to skip a little step here, and we're going to take row 1, and we're going to subtract 4 times row 2, just because it's really simple as well. So what this is going to be is, we're going to add 4 times row 2. We're going to add that. Now essentially what that is we're going to take each of these, and we're going to just add in 4 times whatever is in row 2. So in this case, for the x's, it's 7 plus 4 times 0. For the y's, it is, sorry, I'm doing this in the wrong spot. Up here is where we're doing it. Plus 4 times 0, plus 4 times 1, plus 4 times 0, plus 4 times negative 5. And when we do that, 7 plus 4 times 0 is 7. Negative 4 plus 4 times 1 is 0. 0 plus 4 times 0 is 0. And 41 plus 4 times negative 5 becomes positive 21. And now, if you look at our first row, we have y and z equals 0, and we have a number in for x, and we have a number on the other side of the line. So again, this is pretty much almost the way we want it, except we don't want a 7, we want a 1. So we have to take that 7 and turn it into a 1. So the way we're going to do that is we're going to take row 1, and we're going to divide by 7. So 7 divided by 7 is 1. 0 divided by 7 is 0. 0 divided by 7 is 0. And then 21 divided by 7 is 3. So if you look at our matrix now, we have row 1 in reduced row echelon form. We have row 2 in reduced row echelon form. So we're almost there. So next step, now we need to start getting Z into row echelon form. So now we need to pick another number and make it into a 0. Let's pick this 3. And what we're going to do, again, we got cut off a little bit here. We're going to take row 3, and we're going to subtract 3 times row 1. So when we do that, that becomes 0 that becomes 3 minus 3 times 1. That becomes negative 6 minus 3 times 0. We're just taking the entries from row 1, and we're gonna put them in. Then we get negative 12 minus 3 times 0. Then lastly, we have 27 minus 3 times 3. And when we do that, we're going to summarize that all below in the next step. We get 0, negative 6, negative 12, and 18. Now, if you want, you could reduce this first, or we can just go on and finish it off. Either way works. But let's just finish it off first. So we need to get rid of this -6, and then we got all the non-diagonals turned into zeros. So let's get rid of that. And the only way we can do that is by taking row 2 and adding it on by a factor of 6. So we're going to take equation 3, and we're going to add on 3 times row 2. So it becomes equation 3 plus, 6 times row 2. It's going to be 6 times row 2, and what happens there? It becomes 0 plus 6 times 0, -6 plus 6 times 1, 12 plus 6 times 0. Then 18 is 6 plus 6 times -5. So we're going to add those numbers in. 0 plus 6 times 0 becomes 0. -6 plus 6 times 1, it cancels out, becomes 0. -12 plus 6 times 0 is -12. And then 18 minus 6 times -5 is 18 minus 30, which is -12. So now we're nearly there. We got one more step to do. We just need to take that last row and reduce it down. So we're going to take everything and divide it out by 12, and it becomes -12 divided by 12 is 1. -12 divided by 12 is 1. So in this case, z is going to be equal to 1. So in this case, now we have, if we take this matrix and we rewrite it, the first row becomes x equals 3, y equals -5, or z equals 1. So we conclude with, therefore, the point of intersection is 3, -5, 1. And that's pretty much it. So, like I said, this is not going to be the best solution for everybody. If you're happy with the elimination solution, probably the better one. But I'm a big believer that some people find different methods easier. So if this works for you, then great. Otherwise, it's probably something you're going to see in your first year of linear algebra courses anyways. So it's a good exposure to have anyways, and that way it's not going to be totally foreign to you when you see it a little bit later on. But if you would like to use this for one of your solutions, you're welcome to. As long as you get the correct answer, either method is totally fine by me. You're not going to get any brownie points by being able to do this. As long as you can do one or the other, then you're good to go. All right. Thank you, everybody. And I'll see you in calculus.